Thank you for attending. We have a good online audience as well as quite a number of people in the Nibs Theatre. This is the August meeting of the Stats Society of Australia Canberra branch. I'd like to welcome everyone to it, and I'll start with an acknowledgement of country. In the spirit of reconciliation, the Stats Society of Australia acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay respect to elders past and present, extend that respect to all Aboriginal and Torres Strait Islander peoples. Today, we're on the Ngunnawal and Ngambri lands in Canberra, but there'll be others online in other lands. So today, we welcome two speakers from the ABS. That's Edwin Liu and Nelson Chua. And they will be talking about machine learning in the ABS. The title of their talk is The Practitioner's Guide to Machine Learning Quality in the ABS. Edwin will speak first, followed by Nelson. So I'd like to introduce Edwin and let him take the platform. So thank you.
Yeah, so thanks for the introduction. As mentioned, Nelson and I will be giving a presentation today about a practitioner's guide to machine learning quality in the ABS. But before we begin, just a quick acknowledgement. I would like to thank my colleague, Rebecca Lee, who has played a key role in some of the initial research for this project prior to her rotation as part of the grad program. I would also like to thank Sean Bodsworth and Claire Clark, who have at various points in the project played a key role in some of the high-level project management and project planning. And last of all, I'd also like to thank the whole of the ABS methodology features section, who have given us a lot of very useful feedback over the past year. And that feedback have helped shape some of the contents of the machine learning quality guide. So the machine learning quality guide has four main purposes. First and foremost, it is to help ensure the quality of machine learning outputs that we produce in the ABS. Secondly, it is to help promote more consistency in the use of machine learning in the organization. And this is by creating a common language through which people can discuss machine learning quality, as well as giving advice on how to achieve quality. Thirdly, it is also to help build machine learning capability in the ABS. And lastly, not included here, it is also to help ensure appropriate inputs to any privacy and ethical assessments that we do for machine learning projects. So we have a pretty diverse audience today. Some of us here are from the ABS, but I see a lot of unfamiliar faces. So it looks like there are a number of us here who are not from the ABS. You're either from the Statistical Society of Australia or from the APS data profession. So first of all, welcome. Because it's such a diverse audience, we want to make sure that there's something in it in this presentation for everyone who's attending today. So first of all, if you are from the ABS, just a quick heads up that Nelson and I plan to share this quality guide around in the ABS in the coming few months. And this is to seek consultation on the overall usefulness of the framework of the quality guide. So we're using this presentation, firstly, as an opportunity to promote the work that we've been doing for the past year and to hopefully get people excited about this stuff so that when we do finally share it around, there will be a lot more engagement with it and that it will have a lasting positive impact on the organization. So throughout this presentation, we will be sharing some of the highlights from our research in the hopes that it will get people excited about our work. And to those of you who are not from the ABS, we have come across a number of what we consider to be quite interesting pieces of technical insights that we think will be of interest to a more general, wider audience. And this is stuff that you might be able to take away with you after this presentation and perhaps apply it to your work or to your research. So a bit of context about machine learning in the ABS. We have been exploring machine learning models for about 10 years now. And over this time, we have developed pockets of machine learning expertise all across the organization. So on this slide, I have some examples of some of the models and techniques that we've played around with over these last 10 years, covering both supervised learning approaches and unsupervised learning approaches, as well as a number of topic areas such as regression, classification, clustering, outlier detection, and also not shown here, dimension reduction. It's not an exhaustive list of all the models that we've used. This is just to give you an idea of the variety of techniques we play around with. And the reason we have it here on this slide is to basically justify why in our machine learning quality guide, we decided to focus mainly on model agnostic ideas and recommendations, because we hope that our recommendations will be widely applicable, whether you're using a tree-based model or a neural network, for example. So we've identified a number of dimensions of machine learning quality, but today we're going to cover only a few of the important technical dimensions. We won't be touching on machine learning ethics or privacy, because doing so would actually require a separate presentation. We're just going to assume that those have already been appropriately addressed, and we'll just talk a bit about each of these dimensions that you see here. I'm going to keep the first two dimensions quite short, because I think the last four are more interesting. First of all, for reproducibility, we have put together a checklist in the form of a table with a list of questions that people in the ABS can go through and ensure that they've ticked all the boxes so that their project has some minimum degree of reproducibility. There are various reasons why we want reproducibility. But one of the main ones is, of course, if you have to hand over a piece of work to another team member or another project team, you need to make sure that they're able to pick up on where you left off. So nothing sophisticated here, just something that's pretty cool, simple, and hopefully convenient for people to use. Timeliness covers both technical aspects as well as non-technical aspects. So very similar to the reproducibility checklist, in the technical guide, we have a table that lists out a bunch of ideas for how to improve timeliness for machine learning projects. A lot of these things you will be able to find in the statistical or machine learning literature, as well as in various websites. So I guess there's nothing super original here, but what we've done is we've brought together all these points, collated it into a table so that it's convenient for reference. Now, onto the more interesting bits, interpretability. First of all, what is model interpretability? If you look into the literature, you will probably come across a lot of terms that are closely related to model interpretability. And the most common of these is probably model explainability, or some people abbreviate it as XAI, in other words, explainable AI. But the confusing thing is that different researchers have defined these terms differently. So rather than wrestling with a bunch of different conflicting definitions, I decided to come up with my own definition that I think is most useful for what we're trying to do in the technical guide, as well as a definition that I think is most fit for our needs in the ABS. So I've defined interpretability as the degree to which a human can understand the relationship between the input features of a model and the output predictions. So I'll give you two examples. Let's say you have a model that predicts house prices based on features such as the number of bedrooms, the land size, number of parking spots, and so on. If you're able to say that for a particular house, the predicted house price is this high because of such and such features, like because it's got 5 bedrooms, because it has above average land size, for example, then I would consider your model to be quite interpretable, because you're able to establish a link between the output prediction and the main input features that drive that prediction. Another example is if you fit a model and you're able to say that within this region of the feature space, increasing X would also increase Y, whereas in other regions of the feature space, increasing X decreases Y, then again, I would consider your model to be quite interpretable because you're able to establish a connection between the input X values and how varying the X value will affect the output Y value that comes out of the predicted model. Now, in my mind, explainability actually goes one step further than that, in that not only can you understand the relationship between inputs and outputs, you are also able to come up with a scientific reason or an intuitive reason for why such a relationship might exist and might be true. It's helpful to distinguish between local interpretability approaches and global interpretability approaches. With local approaches, they apply to a single data point. So we go back to the example of predicting house prices. A local approach would help you understand why for a particular house, it has a high predicted value. It's mainly because it has, say, 5 bedrooms and it has above average land size or apartment size. But the key thing here is that it applies only to that particular house, not other houses. If you have another house and you want to understand the prediction for that house, you would have to rerun the interpretability approach for that new data point. In contrast, a global approach doesn't focus on a particular data point. What it does is it tries to help you understand the model as a whole. So rather than saying for this particular house, this is why it's got this predicted value, a global approach would tell you typically or generally, these are the main features that drive predictions for house prices. They are the number of bedrooms and the size of the apartment unit and so on. Both of these approaches are useful. Now, when I looked into the literature, I've come across probably close to 100, 150 different interpretability approaches. And normally, the more options you have, the better. But I think in this case, it's the opposite, in that you have too many options, you don't know how to choose. So in the technical guide, we've decided to focus only on the approaches that are shown here on this slide. We chose these approaches for 3 main reasons. First of all, they are model agnostic. So whether you're using a tree-based model or a neural network, and whether you're doing regression classification, these methods should still apply. Secondly, these approaches are easy to understand and therefore they're fit for our needs in the ABS. Because think about what we're trying to do. We're trying to use these approaches to understand how black box complex models make predictions, right? So if these approaches themselves are hard to understand, then that defeats the purpose of the entire exercise. And lastly, these approaches, I find that they're quite commonly referenced in the literature, and they're also talked about quite a fair bit in various blogs and websites. So chances are they're quite useful. Now I'm going to do a bit of a deep dive into one of those approaches. This is an approach that, from what I can see, appears to be quite popular. It's called LIME, and it stands for Local Interpretable Model Agnostic Explanations. First of all, I'd like to share with you the intuition behind the method. If you have a data set with 2 classes, say a class of like blue data points and then an orange class, and you fit a predictive model to classify data points as either blue or orange, what it does is it creates either a line or a curve of some sort to partition your feature space into 2 halves so that your blue data points mainly fall on one half of the feature space, whereas the orange points mostly fall on the other half. But if you use a black box complicated classification model, you might end up creating a highly complicated decision boundary So in this case, it's a very non-linear decision boundary. For other complicated models, it might also be like non-smooth and quite jagged as well. And that's what makes it hard to understand how such a model makes its predictions. But if you pick a data point, like the blue one that I'm showing here on panel 2, and you zoom into that local region around that data point, you'll see that the decision boundary is actually quite close to being linear. And so what that means is you could approximate the complicated classification model using a very simple one, like a logistic regression model, for example, which ends up creating just a linear decision boundary. Problem is, if you zoom into a local region around the data point, as you can see here, there are only 2 data points, and that's not enough to fit a local logistic regression model. So what we have to do is artificially create a bunch of data points. And in this case, simply by just perturbing that blue data point that you're interested in, using independent Gaussian noise, for example, you throw all those data points into your complicated model and get their predictions. So as expected, those data points that are above the decision boundary, they are predicted as belonging to the blue class, whereas those data points below the decision boundary are predicted as belonging to the orange class. And there you have it, a simple local small data set that you can use to fit your simple model, your logistic regression model, for example. If you fit your logistic regression model, it creates a linear decision boundary that quite closely resembles the complicated decision boundary. If we take a step back and think about what we've managed to achieve here, first of all, the complex model is hard to understand, but with a simple logistic regression model, it's much easier to understand because you can interpret the coefficients, right? If you go back to Stat 101, which I think most people have studied here, we've learned to interpret regression coefficients as with all covariates fixed. If I increase this x value by 1 unit, then on average, the odds of a data point belonging to the blue class increases by e to the power of beta, right? So what that means is with these regression coefficients, by looking at the magnitudes, it tells you how important each feature is in contributing to the prediction for your blue data points. And also, if you look at the sign, whether it's plus or minus, it also tells you the direction of influence as well, whether each feature increases the odds or decreases the odds. So hopefully that was easy to understand. We tried to make the technical guide accessible and readable to a wide variety of audience. So if that made sense to you, that's really good because that was the type of explanation that I include in the technical guide, accompanied with a lot of concrete examples to illustrate how to interpret the outputs. But I'd also like to go through a bit of math as well, because I know some of us here are interested in mathematical details. So if you let F be your black box model, such as your neural network or XGBoost, and you let X be the data point that you're interested in understanding the prediction for, so that's like a blue data point that we zoomed in on, and you let Z be the set of data points that you've artificially created by perturbing the blue data point. Also, because the simple model that we fit can't be super complicated, you might choose to restrict the simple model to, class of linear models or the class of logistic regression models. You have to define what your G is. And you also have omega G here, which measures the model complexity of the simple model. Because the ultimate goal is to understand the prediction for that blue data point that you see there. You don't want to assign equal weight to each of those gray data points. Logically, the gray data points that are closer to your blue data point should have higher weight, whereas those points that are further away should have lower weight. So all your pi(xz) does is it's a proximity measure that helps you calculate weights for each of those data points that you then use to fit your local model. Lastly, you define a loss function, L, which basically, given your black box model F, given your proximity measure pi that calculates weights, your loss function measures how badly your simple model G approximates your F. So up there on the screen, I've included a very simple example of a loss function. This is just a weighted squared loss. But one thing you notice is that inside the square bracket, you've got Fz and Gz prime. The reason the arguments are different is because sometimes when you're fitting your simple model G, you probably don't want to use the same features as your black box model F. For example, maybe your black box model F is using features that are hard to understand in human terms. So you might instead choose a simpler representation of those features. The authors of the paper use an example from text classification. And in that example, Z might be a very complicated word embedding, whereas Z prime is a binary vector of zeros and ones that basically indicate whether each word is present or absent from your piece of text. So that's the idea behind Z and Z prime. And your line basically solves a optimization problem that minimizes the sum of two terms. On the right there, you see the loss function, which is a measure of fit. Whereas on the left, sorry, my left, which is your right, you'll see a measure of complexity. So by minimizing the sum of these two terms, you're basically finding the simple model G, for example, your logistic regression model, that best balances fit and complexity. Yeah, and I have references for this at the end of the presentation, so I'll put that up when we get there. Next, I'd like to talk a bit about accuracy for classification models. Again, the problem with classification metrics is that you have too many options. And when you have too many options, the problem I have with that is I have no idea how to choose what metric is suitable for my problem. So in order to navigate this challenge, I have come up with a bunch of criteria that I think are useful for determining which metric is best for which machine learning problem. And one of these criterion is ground truth versus confidence. Some of you may have heard of this before, but I thought it's worth explaining in a bit more detail. If we use two metrics as our example, recall and precision, if you look at the way in which they're calculated from the confusion matrix, you can view recall as an estimate of a conditional probability. It's the probability that your model will predict positive when given a data point that actually belongs to the positive class. Whereas for something like precision, which you see at the bottom there, it estimates the reverse conditional probability. They look very similar, but there is a subtle yet important difference. They answer different questions. For the first one at the top, it answers the question of, if you're given a positive data point, what is the chance that your model will correctly pick up on that ground truth and correctly predict it as positive? Whereas with the second, the confidence measure, it answers the question of, if it predicts for a data point, it predicts that it's positive, what is the chance that the prediction is correct? How much can I trust that prediction? Or how much confidence can I have? Now, depending on your machine learning problem and the context, one of these might be more important than the other. So anyway, based on the class of interest and based on whether you care more about ground truth or confidence, I have here on the right a bunch of recommendations on what metric I think will be useful for your problem. Just in case anyone is copying things down, either in the room here or online, I'll just leave this slide on the screen for maybe like 20 seconds. Hopefully that's enough. It is recorded, so if you miss anything, don't worry. You can always watch the recording later. I think 20 seconds is on. Now, that was for the case where your data set has no class imbalance. And I'm talking about your training data has no class imbalance. And also the data set that you're planning to apply the model to also has no class imbalance. If you run into a situation where your training data set and the data set that you're planning to deploy your model on have different class distributions, then I have a different set of recommendations. First of all, this is very important. I recommend avoiding metrics that are influenced by class distribution. The reason for this is, imagine if you're using one of these metrics to tune hyperparameters, right? If you had used a metric that varies based on the class distribution, you might end up optimizing your model against a meaningless target. It's a target where the value will change regardless of how your model performs on the new data that you're applying it to. And that change is to potentially merely to the different class distributions of the two data sets. And so it kind of distorts the metric. It distorts the measure, and you can't really see if your model is able to achieve the same performance that you were aiming for when you were training it. There is a reference here that I think is very important. It's by Luke et al., written in 2019. So this is actually one of the main discoveries that I've come across as I was doing this research. Usually when you come across blogs or websites that discuss the issue of class imbalance in the context of classification, they usually use arguments like, here's an example of a confusion matrix. Look, it's very class imbalanced. Let's try and calculate accuracy for this data set. And oh, look, it gives you something that does not make sense. And they use that argument to argue why accuracy should not be used in the case of class imbalance. But for me, I feel like that's kind of incomplete, because when I see that argument, I can't help but wonder, okay, what happens if I tweak the confusion matrix this way or that way? How would that affect the metric? It doesn't help me piece together a picture of how a metric behaves based on the class distribution. Whereas with the paper written by the authors on this screen, they do something very clever, very systematic, and it gives a much better picture of how metrics are influenced by class distribution. I won't include the details here, but just roughly, I'll sketch the idea. What they've done is, for each metric that you see on the screen, normally the formula is written in terms of true positives, false positives, and so on. But what the authors did is they rewrote every single formula to be in terms of something called the imbalance coefficient. And that's essentially just a measure of the degree of class imbalance in the data set. But because they've rewritten the formulas to be in terms of the imbalance coefficient, the relationship between class distribution and the metric is now explicit. And you can study those metrics analytically using formulas, using calculus. You can differentiate and integrate. These are things that you can't do if you just look at case by case. Here's a confusion matrix. Here's what the metric gives. So for anyone who has not looked into this area of research, I highly recommend this paper. Anyway, that's the end of my part. I'm now going to hand over to Nelson, who will talk about the remaining 2 chapters of the quality guide.
Edwin. So moving on to regression, accuracy in regression context. So for the purposes of this talk, when we say regression, we mean a situation where you have a bunch of features X, and you're trying to predict for a continuous response variable Y. So when we think about prediction accuracy, what we're trying to drill down to is the discrepancies between what we predict for y compared to the true value of y. And that difference is known as a residual. So when we try and describe prediction accuracy, we want to try and describe the residuals. So one such way is just to do a one number summary. So an accuracy metric like mean squared error or mean absolute error. And that's useful as a universal approach to compare predictive performance across different machine learning models. If you want to do something a bit more fancy, you could consider what happens to your residuals at different values of, for instance, a feature or the y value. And you might want to identify whether or not you have heteroscedasticity or perhaps consistent biases in your predictions. If we want to take things a bit further, we could also consider putting some probabilistic bounds on our predictions. And that can be accomplished using prediction intervals. So there are many different approaches to constructing prediction intervals. Some that rely on more assumptions than others. But what I'd like to kind of give more of a deep dive in today is conformal prediction, which is a method that has been gaining quite a bit of popularity in machine learning. So just a simple motivating example. Suppose that we randomly select 5 dogs and we record the bark volume of 4 of those dogs. And what we want to do is try and predict the volume of the 5th dog based on the recorded volumes of the 4 other dogs. Now, the idea behind conformal prediction is to construct a prediction interval based on probability statements to do with the ordering of those dogs in terms of volume. So from quietest to loudest. So for instance, in that first probability statement there, it's just saying the probability that the 5th dog will be the quietest of all 5 dogs is 1 in 5 or 20%. And of course, you can say the same thing about it being the 2nd quietest or the 3rd quietest and so on. Now, something to note about these probability statements is that they don't depend on the distribution of y, which makes them distribution agnostic. And this is a key property that is exploited by conformal prediction to construct distribution-free prediction intervals. So what does a conformal prediction interval look like? Well, let's just consider the first 3 of those probability statements. Let's just smush them together and work out the probability that dog 5 is either the quietest, 2nd quietest, or 3rd quietest. That's just the sum of the probabilities, so 0.6. Now, if we use a bit of logic, we can massage the probability statement in a way where we have y5 being sandwiched between 2 values, and those 2 values are a function of your observed data. And so that's known as a prediction interval. But the idea is that if we have observed data, we can plug in those values into our expression for the interval, and that gives us our prediction interval for y5. That 0.6 that we calculated earlier, that's known as the coverage probability of the prediction interval. And something also to note is that we actually had some control over that coverage probability. So in the example I showed you, I took 3 of those probability statements from before, but we could have just as easily taken 4 of them to construct a prediction interval with a coverage of 0.8. So another benefit of this conformal prediction framework is that you have control and you have an explicit exact value for the coverage probability, even in finite sample situations. So the things that I want you to take away about conformal prediction are that it gives you distribution-free prediction intervals, and also you have finite sample coverage. So in that example that I just illustrated, we had a situation where we were randomly selecting dogs independently of each other from the same underlying distribution. So the dogs were IID. But it turns out that this idea of constructing prediction intervals based on orderings of the random variables is also applicable to a broader class of random variables known as exchangeable random variables. For the purposes of this talk, all you really need to know about exchangeable random variables is that they're allowed to be statistically dependent, but the form of that dependence is limited. And we'll see why acknowledging that exchangeability can be used to construct these prediction intervals is useful in just a bit. So just kind of a broad layout of how you would do conformal prediction in general. First thing is that you would specify all the variables at your disposal. So what you observe as well as what you're trying to predict for. In a regression setting, where you have IID observations, but you might have like 49 XY pairs that you observe, and you have an X for your 50th observation, but you're trying to predict for the Y value of that 50th observation. Now, if you compare this to the motivating example, it's not that easy to kind of order these Z pairs of observations directly, these XY pairs. So in general, what we need to do is we need to apply some kind of transformation to the data in order to get these univariate exchangeable random variables. And once we have those univariate exchangeable random variables, we can then construct our prediction interval based on orderings of those random variables. So to give you a more concrete example of this, we have what's known as full conformal prediction. And so the idea is that we fit any kind of IID assuming regression model to our data, in particular an augmented data set, which doesn't just involve the observed data, but also this unknown 50th data point. And so this might sound a bit weird, but just bear with me for a moment. Now, it turns out that the residuals of this augmented data set model are actually exchangeable. Something to note is that they aren't actually IID though, because all of these residuals have a common source of dependence on the augmented data set model, right? Because the augmented model is a function of the observed data and this prediction target. But nevertheless, since these residuals are exchangeable, we can apply that idea of conformal prediction to construct a prediction interval. And as you see it right there. So how exactly would we obtain the prediction interval or compute it? Well, you can see that it's actually expressed in this kind of implicit form. So what we would need to do is actually this kind of trial and error process where we would get some trial value of Y50, fit an augmented regression model based on that trial value, and compute the residuals of that model. And then once we've got the residuals, we would see whether or not they satisfy the set condition at the bottom there. And so we would have to do this over and over for different values of Y50. And then our prediction interval is just the set of values Y50 that satisfy the set criterion. So this means that full conformal prediction can be quite computationally expensive because for every kind of test value of Y50, you have to refit a regression model and recompute residual. Now, as an alternative to full conformal prediction, we have what's known as split conformal prediction, where instead of fitting a regression model to an augmented data set, we just fit one by firstly splitting the observed data into a training set and a holdout set. We fit a regression model to just the training data set, and then we compute residuals based on just the holdout set. Turns out that the residuals from just the holdout set are also exchangeable. And so we can go and construct a prediction interval based on these residuals. Now, this time, we actually have a closed form expression for our prediction interval. So this is a lot more computationally fast because not only do we only have to fit a regression model once, but we also have a closed form expression for the prediction interval. Now, just to kind of illustrate what these prediction intervals look like, here I've just got a simple simulated example. So simple linear regression, the true relationship is y equals 0.5x, and we've got IID standard normal residuals. Now, just as a baseline comparison method, here's a parametric prediction bands. So this prediction band is centered around our ordinary least squares fit for the data. And the prediction bands, you can see have a slight curvature to them. So under the assumption that our data really do follow this model with standard normal residuals, this prediction band can be thought of as like a gold standard approach in this particular scenario. Now, compare this to the full conformal prediction band. It actually looks quite similar to the parametric prediction band. And in fact, it also has that kind of signature curvature to it. Now, I guess the miraculous thing about this is that with this full conformal prediction band, we made no distributional assumptions about y. And I guess the added advantage of not making those assumptions is that we have a prediction band that is distributionally robust in the sense that even if the residuals don't turn out to be, for instance, normally distributed, they could be t-distributed for all we know. This full conformal prediction band still gives you your guaranteed 80% marginal coverage, whereas the parametric prediction band under that normality assumption doesn't do that. Now here we also have the split conformal prediction band, and this looks quite different to the other two. So it's centered around this regression model that we fit just to the first 25 data points, so our training data set. And it has a constant width at different values of x. So this kind of exemplifies the fact that although conformal prediction can give you these coverage guarantees, which this split conformal prediction does, the quality of the prediction interval very much depends on your choice of conformal scores. And just to kind of hone in on this point further, we could fit a different kind of regression model rather than least squares. We could just fit like a 5 nearest root neighbors regression model, and we get some kind of different prediction interval. So because conformal prediction isn't like a thing that's going to miraculously solve all your problems, you still need to be very careful about your choice of conformal scores and your choice of regression model. All right, and lastly, I'd like to cover the representativeness aspect of machine learning quality. So I'll be describing things more so in like a supervised learning context, but of course these ideas can be more so, some of these ideas can be more applicable to unsupervised learning as well. So what we mean by representativeness is this kind of notion that our observed data ought to be aligned with our objective or what we're trying to achieve with our machine learning. So for instance, that could be prediction or estimation of prediction metric, accuracy metric. A lot of the standard machine learning methods that have been developed rely on that assumption that there is this alignment between our data and the objective. But if we don't have this alignment, then we might run into issues such as biased predictions or misleading estimate of prediction accuracy. So what kind of representativeness issues might we run into? Well, for one, we could think of our observed data as coming from a larger source population. So for instance, if we ran a survey, then we might run into issues with the sampling biases and response biases. If we have admin data, we could also run into coverage issues. Another representativeness issue is if there's some kind of misalignment between that kind of source population and this other population that we're trying to adapt our machine learning model to, and this is known as distributional shift. So if we do have these kinds of representativeness issues, we might want to consider making some kind of adjustment to our observed data so that it's kind of more representative of our prediction population before we then apply machine learning methods that are standard. I think it's also worth acknowledging a different representativeness issue, which is class imbalance. So just as Edwin mentioned before, now with class imbalance, it's a bit different to the other two in the sense that if our observed data is indeed kind of reflective of the underlying distribution of our prediction population, class imbalance by itself is not an issue. It's only an issue if you're more concerned about accuracy in like one class compared to the other, for instance, right? Like you might be more interested in correctly predicting positive cases rather than correctly predicting negative cases. If you have a, so the only real situation where you'll be considering class imbalance is if you have some kind of cost-weighted learning kind of situation. Yep. So I regard class imbalance more so as kind of an intra-distributional representation issue, an issue that affects representation within a data set, whereas the data collection mechanism issue and the distributional shift issue are more like between distributions, so inter-distributional. In the machine learning literature, you often find that these interdistributional issues are kind of clumped together. They are really kind of distinguished, but for the purposes of the ABS work, this distinction kind of gives us a bit of more of like a nuanced view on the issues of representativeness. And also, if you're familiar with the total survey error framework, this is just basically part of this, just adapted into that machine learning context. So just a bit more on interdistributional shift. So we might want to actually first detect whether or not we even have a distributional shift problem. So ultimately what we're trying to do is kind of detect whether or not we have equality between two distributions. So very simple descriptive way of doing that is just to produce some plots or summaries. If we want to be a bit more formal, we could do some kind of hypothesis testing. And if we want to do a machine learning type solution, we could consider stacking the two data sets that we have together, labeling them based on their origin data set, and building a classifier to try and discriminate between which observations come from the source from one population and which one comes from another. And then once we have this kind of binary classification model, we could apply some interpretability methods to see which of the variables are explaining this model the most. And those would kind of tell us which variables have shifted the most as well. Now, of course, all of this is kind of easier said than done, because in a lot of cases, we might have some variables in one data set but not in the other. A very common situation you'll be in is that you won't have Y for your target population. I mean, if you did, then what's the point of doing machine learning? So you might only be able to do these kinds of shift detection methods on a limited subset of variables. And now if you do detect a shift, then you might want to correct for it. So for instance, our objective might be, rather than optimizing or minimizing empirical loss on a data set with respect to the observed data, we might want to do it with respect to the target distribution. So there are a few methods in machine learning literature to do this, known as domain adaptation methods. But I caution against using them too liberally, because they generally rely on rather strong assumptions about the nature of the distributional shift. So really, this kind of hones in the point that ultimately it would be very valuable to get some kind of source of ground truth data, with which we could either both better detect distributional shifts and also to better kind of validate certain assumptions that you're using when you're using methods. And I think the ABS is kind of better placed to do this kind of thing because we can collect data as well as integrate existing data sources. But of course, data acquisition is expensive and time consuming. So things like this should be factored into a machine learning project during the planning stages. Worst case, so we could just consider not correcting for any of these shifts issues, but at least acknowledging these issues when we're kind of describing our outputs and describing the quality of our outputs. And also we should also temper our expectations with how the outputs should be used. All right, I will hand over to Edwin to have some concluding remarks.
So yeah, just a quick update on the progress for the project. So like I mentioned earlier, we are planning to share the machine learning quality guide in the coming months, but that'll be within the ABS. And the purpose of that is to do a first round of internal consultation to get feedback on various aspects of the quality guide. So things like readability, relevance, accuracy, and just overall usefulness. So at the moment, we are doing a review within just our ABS methodology features section. Later on, that will be shared around within the ABS methodology and data science division, and eventually also to the broader ABS. So keep an eye out on that. As for external people who are not from the ABS, like I said, unfortunately, we can't share what we produce externally, not at the moment. But if you have any feedback for us, or if you're interested in any of the work that we've done, feel free to get in touch and just contact either myself, Edwin Liu, or my colleague, Nelson Tra. And you can do this by emailing methodology@abs.gov.au. So yeah, question time.
Thank you. Very interesting, stimulating talk. We may have questions online, we may have some at the floor. So how about we start with any questions of people who are present here? Yes.
I'm interested in the line. So earlier on about size 20. What's the advantage of using like a perturbation or randomness around the point of interest rather than like systematically constructing a grid of plausible sort of features?
For the benefit of the people online,
Yeah.
the question that can you people online hear that question?
No, we couldn't.
All right. All right. So if I can, well, can either of you paraphrase the question, or I'll do my best. For the line method, you select a cluster of points around a point randomly, and the question is, why do you do that in that procedure? So is that sufficient summary? Right. Edmund.
Yeah. Can I go back to the slides? Oh, okay, yeah. Yeah, so this part, right? You're wondering why in panel 3, rather than just doing a grid and just creating data points over that grid, why we instead choose to randomly perturb data points based on the point of interest. Yeah, I gotta be honest, I haven't actually looked too deeply into this method. The only paper that I've read is the paper written by the original authors. And in that context, they were actually describing the line method in the context of text classification and also in, I think, image classification. So when they described the method, they actually kept the methodology quite general. So instead of actually recommending a particular perturbation method, creating these artificial data points, they described them more in a more abstract way. It's like you just want to create data points that are independent of the data set that you're looking at, and also that has to be model agnostic. So what I've described here is actually just a simple example to illustrate that idea. Of course, if you find it useful to create data points using that grid system that you just described, it could be useful.
I guess I could just imagine a world where you would add noise and get something that was ridiculous. You know, a house with 5 bathrooms and 2 bedrooms. Text that doesn't make sense.
Yeah.
And in which case, perhaps your model is not very like, you know, even your simple logistic regression is kind of meaningless.
Yeah, that's right. That is in fact one of the weaknesses that was described by the paper, and also in various other sources. It's the fact that when you're creating these artificial data points by perturbation, it often ignores any kind of relationship between the features that you're perturbing. So exactly as you described, in some instances where these feature values are correlated, you might actually benefit from using a different perturbation mechanism, one that perhaps takes into account the local covariance structure. And yeah, for example, you could just look at nearest neighbor points close to the blue data point of interest and use that to estimate some kind of robust covariance matrix. And I don't know, maybe use a Mahalanobis distance as your the weighting function for the proximity measure. So yeah, it's quite general, quite flexible, and I'm sure different implementations of Lime will probably do things differently and have different options.
Yes, next question.
First of all, fantastic talk, both of you. In the process of constructing the guide as it is now, although noting that there's still some consultation phases to go, is there anything that at the outset you thought was going to be perhaps more important, and as you did the work, was like less important in the guide, or conversely something that wasn't that important in your eyes at the outset became more important as you progressed?
We repeat the question for them. The question was, in constructing the guide that they've been working on, is there anything that's become more important in the process compared to what they thought at the beginning, or the other way around, anything that's become less important as they proceeded compared to what they thought would be in the beginning? So is that correct?
Yeah. Thank you. I can answer it. But I'll give it a go first. So when we initially started creating this technical guide, our idea was that we didn't want to wait until the end when we have a first draft ready before we start sharing this knowledge. So in fact, throughout the past year, when we were working on this, we've actually been doing regular presentations within our section and sharing knowledge as we go. So that said, when we first started off on the number of dimensions that we presented here, we actually thought things like accuracy and interpretability were more important, simply because there were members of our section who were playing around with machine learning methods at the time, and they needed to know how to make the model more accurate. They also needed to understand, the outputs that come out of the model. Why did it make these predictions? So yeah, we did think those dimensions were more important. We focused on those first, and we shared knowledge as we went. Now, in hindsight, do I think any of these are more important than the others? Haven't really thought too much about that. I would guess, accuracy is first and foremost the most important. There are other dimensions like reproducibility and timeliness, which in the ABS we are already considering to some extent already. So yeah, I think if I were to rank it now, probably accuracy followed by explainability. And then some of the other dimensions like representativeness, followed lastly by timeliness and reproducibility, which are sort of like equal. But yeah, that's just in my view, right? So Nelson, if you have.
Yes.
Thanks. I echo your comments about a great presentation. I'm from the Australian Climate Service, which is a partner of the Bureau of Statistics with the Bureau of Meteorology, Geoscience Australia and CSIRO. I've been listening to similar presentations across each of the partner agencies about their approaches to machine learning. And so just wondering if there is some element of practice sharing that could be possible or to be explored, and some interesting interpretations of machine learning happening in other areas of the Bureau of Statistics. So I'll be interested to see, where this collaboration element.
Just to repeat the question, a question from a lady from Australian Climate Service, observing that there are other agencies and other areas possibly of Australian Bureau of Statistics are looking at machine learning, and is there some sort of sharing for commonality of practice and collaboration going on? Is that sufficient?
What plans once you move this forward? That's it. Thank you.
Okay.
Yeah, thanks for that question. So when we started on this project, we of course didn't want to just reinvent the wheel. So in our literature review, we actually had a look at some of the things that other agencies are doing, not just within Australia, but also internationally. So other national statistics as well. Like we know that Statistics Canada, for example, have developed a framework on responsible use of AI and machine learning. We also know that I think the ONS, that's the Statistics Office in UK, have also collaborated with the United Nations Economics Commission for Europe to create something similar as well. And we actually drew a lot of ideas from that. As for ongoing into the future, any plans for knowledge sharing? Certainly. We are actually currently actively involved in a number of discussions that are taking place, and they're organized by the United Nations Economics Commission for Europe. That's a long name. But yeah, we meet pretty much every month to discuss topics around like machine learning ethics, privacy, around interpretability, and so on. And we're actually working with them to hopefully in the near future create something that's like a I guess like an international framework on responsible use of AI and machine learning in national statistics offices. Does that answer your question?
It's great to hear the collaboration.
Well, we see if there's any questions online now. Has anyone got a question who's online?
Yeah, Warren, this is Xiu Ming, XABS. May
Yes.
I ask a question? In fact, I want to make perhaps a comment, and then afterwards I'll ask a question of Nelson and then a question of Edwin. First, I'd like to congratulate ABS for doing this piece of work. It's extremely important, I think, as we're moving into the machine learning space. And I think, Edwin, you did make reference to a UN ECE project on machine learning. They've actually published a publication on responsible use of machine learning. It was an international project with, I think, representations from ABS, Stat Canada, ONS, and Statistics Netherlands. So it's I think the lady actually asked for a reference or something that's a useful publication that is available in the public domain and people can refer to. My other comment is in relation to the representativeness of the training data set. The misalignment of the training data set and also the target population is not only an issue for machine learning algorithms, but it's also an issue for the classical statistical algorithms. So if you have if you train your regression model based on a training data set that is not representative of the prediction of the target population, you run into similar problems. So, and I think that it's good that you raise the issue of representativeness in machine learning, but I think the similar point can be made for classical statistical algorithms. Now, my question to Nelson is that the conformal confidence interval, conformal prediction method is interesting, but I just can't see its application in official statistics. If I understand it correctly, you are trying to predict either, a data point is the 5th biggest data point or the 5th smallest data point. If that is the case, then I just cannot see how that method has application in official statistics. Now, my question to Nelson is actually, to Edwin, is actually a follow-up question that was asked before. My understanding of your interpretability is to try to get a attributable model to approximate the black box model. But I don't understand why you are comparing the difference square between GX and GZ and FZ dash, and not comparing GZ with FZ square. So that's my question.
Thanks, Xiu-Ming. So regarding your question about applicability of conformal prediction in the ABS, so right now, like this method kind of only gives you predictions at like a unit level or like based on record level. So it could have limited usability in the ABS if, for instance, each data point represented a small area and you built a regression model for small areas at that area level. So then you'd have a prediction interval for a given area, SA2, for instance, and that could be something you could potentially publish. But kind of more generally, you might be considering a unit level model where units represent households or businesses, and we might be interested in a prediction interval for an aggregate quantity like an area level mean or area level sum. And in that space, there definitely needs to be more work done in literature for conform prediction. Conform prediction is a rather kind of new kind of technique. And so there's a lot of active research going on in the space.
Yeah, I'm just going to go back to the slide where I showed the loss function for y. Yeah, so Susan, you were talking about this slide, the example of the loss function I gave, right?
Yep.
Yeah, what was the question again? Sorry.
Why are you comparing fz with gz dash and not comparing fz with gz? So my understanding is that you're trying to use g to approximate f, where g is interpretable, right? And therefore you should be comparing, I think, the predicted points, right? So is the dash gz, should gz dash be read as gz?
Oh, okay. Yeah, I got the question. So yeah, I think in many applications, you're absolutely right. There is no reason why z prime or z dash should be different from z. You can actually have z in both arguments for both your f, which is your black box model, and g, which is your simple local interpretable model. So the authors introduced z versus z dash because sometimes the features or the variables that you use here in z for your black box model f might be quite difficult to understand in human terms. So in that case, when you're fitting your local simple model G, you might use a simpler representation of those features. Yeah, it's a good example I can give. Okay, yeah, here's one example. Now, of course, this is just an example. The methodology is quite general, so depending on the situation, you might choose to do things differently. But one example is, if you're using a black box model like a random forest that has, I don't know, 100 different features, right? When you're fitting your local simple model, you probably don't want to use 100 features because the more features you have, the harder it is to interpret. So in that example, Z prime might just be a subset of your Z. You can select this using variable selection techniques like lasso regression, which is where you just regularize your logistic regression by the L1 norm of the coefficient vector.
Yeah, that makes sense. Thank you, Edwin.
Yeah.
Are there any more questions online? How about in the audience at the Nibs Theatre? Right, well, it looks like we're pretty well wrapped it up. I'd like to thank Edwin and Nelson again for a very interesting talk, and there's been some interesting questions, and thank everyone for attending. Our next meeting of the Statistical Society of Australia Canberra branch will be in early October. So just, if you remember, keep an eye out for the emails for that.